Welcome to Spring LIB.
Here we kind of have kind of an obligatory problem that is in almost every physics book of a box or a particle or something, block, spinning around on a table that's attached to a string here. So the string keeps it going on this circular path. But the string goes through a hole, and we can actually pull on this string to shorten it. Well, we could actually let it release some of it and let this thing, the radius get larger. So what happens here is they ask us, let's see here, they tell us that the block weighs 0.025 kilograms. The radius to the initial radius is 0.300 meters. And the initial angular velocity is 2.85 radians per second. And then they tell us that we pull this string down so that the radius now becomes half of what it was. So the radius becomes 0.15 meters. And so they ask, is the angular momentum of the block conserved? Why or why not? Well, it is, because the only force acting on this block, well, the forces acting on this block are gravity, or its weight, and the tension in this string. And both of those don't generate a moment about the axis about which it's rotating. So we have no moment about that axis of which it's rotating, which means that its angular momentum should be conserved, because there's no tau about the z-axis, if we call that the z-axis. So we can say, okay, what is the initial angular momentum? Well, it's you can think of this, well, either the mass moment about the rotation axis here times the initial angular velocity, and then after that has to equal the angular momentum after we've pulled the string in. So that now the mass moment has changed. So that's mr1 squared, and the angular velocity then also has changed. So we can see if we solve for omega 1, we get the quantity r dot over r1 squared omega naught. This happens to be 4, so the angular velocity is now 4 times what it was, or 11.4 radians per second. So the angular velocity increased by a factor of 4, although we only decreased the radius by a factor of 2. So then they ask us about the kinetic energy. Well, we know, the kinetic energy we can write out. And we can see that initially the kinetic energy is 1/2 mr0 squared omega squared. And that winds up being 0.009138 joules. In the second case, after we've pulled the string in, J has gone down. J has gone down by a factor of 4, right? Let's see, yeah, J, because this went down by a factor of 2, so square. But this went up by a factor of 16, because this went up from a factor of 4, and now we're squaring it. So this winds up being much larger than this, and in fact it's 0.03655 joules. So the change in kinetic energy is the difference, this minus this, is 0.0274 joules. And so they ask us, what work did we do on pulling this string? Well, that's just because there's no change in gravitational potential, because we're assuming that this all stays in the same plane, horizontal plane, that the work that we did in pulling this cord is just what was gained in kinetic energy. And so that is 0.0274 joules of work we did by pulling this cord, and which also we could figure out, if we assume that we apply a constant force, then we could figure out what that force was, because we know how far we've pulled the string down, or the distance through which that force has acted. So anyway, basically when you do this, you have to do some work to get this to come in farther and farther. You have to do more and more work. And then obviously as it gets in very close to here, theoretically the work would go to infinity, right? Because r goes to 0. But in that case, we'd have to say this block is actually three-dimensional, and it has some rotation, some mass moment about its own center. We can't just call it a particle anymore.